Last time we saw each other, I left you with this picture, right? So let's talk about it. Okay, it won't take too long, but that's me. That's Larry Cooper. That's Nathan Mantell. This is 1980, roughly, okay? And at that time, you can hear me okay? And by the way, I always say this, is it loud enough? Am I loud enough? And then I usually refer to my shirt, okay? Because I'm wearing a different shirt every day, so I have a lot of shirts. Any case, in 1980, I was Larry Cooper and I and Hal Morgenstern, who was at one point, well, at that point, he was actually a PhD student in the epidemiology department at UNC in Chapel Hill, where I was. We were near the end of finishing this textbook, a textbook called Epidemiological Research, Principles and Quantitative Methods. It actually was in some sense, it was I may have mentioned this before, it was the sort of the first textbook that came out that sort of covered modern epidemiology. And I know some of you are familiar or have looked at Rothman's textbook. That came out later, okay? But we were the first, not, in some sense. And that textbook was in some way, the forerunner or the basis of what's now Active Epi Web, which is a 21st century version of what was in that textbook. But in 1980, we were near the end of the textbook and we were about to write a chapter. We were at the point where we were talking about logistic regression. We had written the chapter about the theory of logistic regression, or what the model looked like, how you test hypotheses, how you estimate odds ratios, which are all the things you've just been dealing with in the last couple of weeks, right? And reviewing from last semester. We wanted to write a chapter about this issue that I mentioned at the end of the class last time of, well, how do you come up with the best model? How do you, given a situation where you've got one or more exposure variables, you've got variables you want to control for, some of them might be confounders, some of them might be effect modifiers, you got a health outcome, you want to somehow do a model, because if you tried to do stratified analysis, you'd have all sorts of zero strata, you'd be running out of numbers and stuff. So we wanted to come up with a way of saying, well, how do you go about this process of coming up with the best model? And there was this week where Nathan Mantell was visiting Chapel Hill and giving a lecture, and Larry Cooper and I had the opportunity of having a private chat with him. So he came to my office. And so after a few introductions, and this guy at that time, still now, although he's passed away, is a guru. He's done a lot of things. The Mantel-Hansel test, it's named after him. I don't have a test named after me, never will. So, but anyhow, we had the opportunity to ask him, and this guy knew all about everything. So we sat down and we fairly quickly, we asked them, well, look, we're in a situation where, and I'm sure you were many times, where you had the situation where you were trying to come up with the best model. What would you say about how to go about that process? That's what we asked him. That's what we were there to do. And his answer was, it's an art. And it was a very short meeting, because we tried to pin him down some more and say, well, what would you say about, could you give us a little bit more details about how you would go about, where does interaction fit, where does confounding fit, how would you do it? And he basically said, well, I sort of feel my way around. I've been around a long time. I know what to do, and I do it, and I wouldn't want to write anything down. And that was the meeting, pretty much, goodbye, or thank you. And so he said it was an art, and at this point, Larry and I were left as sort of you might say, the budding artists. How are we going to, should we even write a chapter when this guy said there's no way to write a chapter? Okay, so that's where this comes from. And so what we decided to do after all was said and done, we said, well, people have this problem. all the time. And you still have this problem where you have a lot of data, you have a lot of variables, you want to come up with a conclusion and answer to a question, and it's a mess. How do you go about that? And just to say it's an art and leave it at that, well, it is an art in a sense. There's a lot of artistic things that you have to do in trying to figure this thing out. But there ought to be something better than just saying it's an art. And so we decided we were going to write a chapter and add it to this textbook about how to do this, or how to go about the process. Now, we realized, especially based on what Nathan Mantell said, that writing a chapter wasn't going to be that easy because we could clearly see there was art involved. I mean, it wasn't that clear that you could say this is a mathematical way to go about doing it. There's a strict rule to do it. So in writing a chapter, we sort of decided that what we were going to have to do is not write rigid rules, but to be able to write some guidelines as to how to go about that process. So that's what the chapter was all about. And that's what in the textbook you have now, the logistic regression textbook, that's chapters, I think it's 6 and 7, that deal with this modeling strategy issue. And actually, chapter 8 now, which was added in the 3rd edition, is also dealing with modeling strategy and a few other things, but it's primarily modeling strategy, and it's dealing with the idea of guidelines. So that's where this story comes from. Big deal, okay? So what we basically are going to be talking about here in the next couple of weeks is modeling strategy guidelines, how you go about this process. And it's not going to be a set of rules that you have to follow exactly like you do. But I've been teaching this thing, and since we wrote this thing, that was a long time ago, before many of you were born, right? And I've been teaching this and using this, and I haven't really changed my mind about this strategy. And Larry is older, even a couple of years older than me. He hadn't changed either. And a lot of people are using this and again, it's guidelines. So there's a lot of leeway in here on how you go about the process. Okay, so that's the main point of what I want to say here. So, in fact, the guidelines basically say if you're going to go about the process, there are 3 primary stages that you have to go through. It's a 3-stage strategy. And I'll list the stage. I'll talk about the stages in a moment. But the goal is to try to get a valid estimate of the exposure-disease relationship. Okay? Now, what I mean by that is, well, first of all, it sort of says that what you're trying to do when you're dealing with this problem is you usually have a question. You're doing a study. You're doing the study to evaluate some kind of research question. And typically, as we've been talking about in this course, as Eli even started off when he started his review, typically the question involves a health outcome, if you're talking about epidemiology or health research, a health outcome, and one or at least one, what we call an exposure variable or important predictor of that outcome. We want to see if the exposure variable helps to determine or cause or predict the disease, and we typically want to control for some other variables. Okay, so that's the question. The question is there a relationship between exposure and disease? How strong is it? Is it significant? And, can we do a good job of pinning it down? That's sort of the idea. We want to answer a question. So this is in order to answer the question, we basically want to get the right answer. That's what we mean by valid. We want to get the right answer to whatever question we're dealing with, okay? And what this sort of means in terms of what we've been talking about up to this point in the course and even last semester was what we mean is we want to be able to say something about the ED relationship, and we want to take into account the problems or the issues that we have to deal with when we're doing that. One of them is confounding, because this has to do with one of the issues when you're controlling variables. One of them is effect modification, or its statistical related component interaction, and the other is precision. So the goal of what we're going to be talking about here is trying to come up with the right answer, a valid answer that takes into account confounding, interaction, and precision in some reasonable way. That's the idea. Okay? Got that? Okay, but what it's not doing, what it's not saying, and I go to a couple pages later, well, this is a little background about how when you read stuff in papers and you look at a paper that somebody's written where they've done a study, you don't often see a lot of information about how they did what they did. And you can't often figure it out. And as I say, information is often not provided. Okay? So one of the reasons for trying to have a strategy is trying to pin down, when you read something, try to figure out what they did. But more important than that is for you to have a strategy when it's your turn to do the analysis. So, but the point I'm trying to say here is one goal of an analysis when you've got a lot of variables and that you're dealing with epidemiologic or health science data is to get a valid answer, get the right answer to a question. Another goal is simply to get a way of predicting the outcome from whatever you've got as predictors. And they're not really the same goal. If your goal is prediction, what you're trying to do is get the right answer. You're trying to use the predictors, the E and the C's, to try to see how closely you can get to whatever the value is of the outcome variable. You want to predict the outcome variable. But that's not necessarily answering a question about whether one variable is related to or a strong association or even a causation relationship to an outcome variable controlling for other variables. So prediction and validity are two somewhat different things. So if your goal was prediction, you wouldn't necessarily want to do what I'm going to be talking about for most of these next couple of weeks. In fact, when you took the course from, I guess it was Bob Lyles last spring, and you were using the other book, the regression book. In the regression book, there's a chapter about I guess it's, I don't know whether it's called modeling strategy or how to get the best model or something like that. And in that chapter, there's a discussion of how to go about getting a best model if your goal was prediction as opposed to validity. And you may remember something from that course where, I don't know, I'm sure Bob talked about that. I'm sure it was different ways like backward elimination and forward regression and step. Remember that? Okay, so those were ways where you would sort of do something where, you remember there was something called R-square? Remember R-square? R-square was the total way you can explain the outcome from all the variables in your model. And the highest R-square you could ever get was 1, and the lowest is 0. And if the closer R-square is to 1, the better the model is doing and explaining everything that's in your data, right? And one of the ways to do prediction is you say, well, I'm going to get the model that does the best job of getting the highest R-square, or it's somehow the best model that I could use, the most efficient model, maybe to get the highest R-square. Well, that's not answering the question about whether there's an exposure-disease relation. This is trying to predict how well you can get, you can predict Y from the X's. So prediction is a different goal, and you would do it a different way as described in that chapter. When you're talking about validity, which is again going to be our focus, which is the primary focus of a lot, not everything that's done in epidemiology or in health science or medical science, but that's what you're trying to do when you're looking at what's called etiologic research. We're looking at cause-effect relationships, so that's validity. Standard computer algorithms like backward or forward, they're not going to answer the question. They're missing something. They don't necessarily properly deal with confounding or interaction. If you just say, oh, I'm going to do backward elimination and see what I get, or something like that. Or I do forward, it's not elimination, forward addition. We're going to be talking about validity here. Questions so far? Again, I realize it's hard to ask a question in this big room. So here are the 3 stages. Okay, three stages are variable specification, interaction assessment, and the third stage is sort of a combined stage of confounding followed by precision. Those are the 3 stages. Okay, so what I'm saying is these are the guidelines. If you've got a situation as you have some data, you got a bunch of variables, you got an E, at least one E, you got several C's, you got a health outcome, and you want to come up with the best model, you have to consider these 3 stages in going about the process. Now, how you approach these 3 stages might vary depending upon who you are, who the people you are working with, what data you're dealing with, what your questions are. So I could have the same data set, I can give it to everybody in the class, and you all might feel comfortable to some extent what I mean by guidelines after we start talking about it, but you all might make different decisions along the way in how you work with the guidelines. So that's why it's not really a rule, it's a way of going about how to go about it, but it won't necessarily be that everybody will get the same answer. Hopefully, if you do it reasonably well, you're all going to get pretty much the same answer, but there are different decisions you have to make along the way. So this is something that makes you wonder a little bit about anything that you read anywhere. When somebody writes a paper, whether they did anything, they did it their way. Well, what if I did it my way? You know that song, there I did it my way. Would you get the same answer? And you worry what people do, and you should worry about that. I mean, it may even make you feel that maybe you ought to become a taxi driver or something, and do something different than get in this field, because there's a lot of things to worry about whether you can, and this is the hardest part. That's why Nathan Mantell said it was an art, because there is art parts to this. Okay, so here are these 3 stages. Now, the order in which I've listed them is the order in which you should do them. You should do variable specification first, whatever that is. You then should do interaction assessment, and then confounding followed by precision. We're going to talk about each one of these stages. Okay, that's what we're going to do. This is the order. Okay, now what I want to then do, but I haven't talked about, well, why this order? So let's talk about that. Again, this is a common sense idea in terms of how to go about this process. The main reason for variable specification, first, is that when you're trying to fit a model and you've got some study question, you've got some variables you measured, you don't want to throw into the model a whole bunch of things that don't make any sense. You want to start off with a model that makes sense. That's the idea for variable specification first. Okay, that's the main thing. Variable specification ought to be first. You don't just throw anything in there. Once you do that and decide, now how you decide what makes sense, how do you decide that? How do you decide that? I mean, given that you have this outcome, there's a certain illness, a cancer, and you have an exposure variable, certain treatment or something like that, and and how do you decide, and then how do you go about this process? How do you decide what to specify or how to go about this thing? Well, you have to read the literature, or you have to know what you're talking about. You have to know something about the disease and what's been written about it, not only in the literature about what's been sort of shown from studies, but also what conceptually makes sense. So it's not just what's been shown. Some of the variables you might put in the model are things that maybe conceptually ought to be in there as variables you control for, because that's what the literature says. They may not have shown it, but it might make sense. So the literature has a lot to do with variable specification. In fact, there's another thing that has a lot to do with variable specification. We'll talk about, in fact, I'll even jump to that now. Do you remember all that stuff you learned about DAGs, which you loved so much? Right? Well, where that comes in more than in any place else is in this variable specification stage. That's where when you start thinking about you should start thinking about it in the design in terms of how you're going to do the study and what you're going to measure and all of that. But when you start getting down to the analysis, you better think about, well, what's your DAG? In terms of that's going to help you decide what should go in that initial model. You're not going to put certain things in that initial model to control for if your DAG suggests that you shouldn't control for. Give me an example of that you've learned from the Dr. Howard's Penny's course last semester. What kind of variable don't you want to put in a model that you don't want to control for? What's it called? An intervening, or I don't know what it's called, intervening variable that's in the pathway between exposure and disease? Because if you control for it, you're going to find that if you control for it and trying to find the exposure, you're going to actually find that there's no relationship if it's an intervening variable, and that's not what you want to do. You want to see if there's a relationship. If it's in the pathway, there won't be. So you don't control for intervening variables. So you better think about whether the DAG suggests that it's an intervening variable or a confounder. And now you remember, in fact, I'll show you some quick pictures of that. By the way, am I talking fast? Well, you know, what are you going to say, you know? I'm from Brooklyn. We talk fast in Brooklyn, you know. And I've been south for a while. Okay, so DAGs. Remember DAGs? Remember that? This is, whoops, did I want to? This is not everything about DAGs. DAGs and modeling strategy. Where it comes in, I'm going to go back and forth a little bit. Where it comes in, and this is not a lot in this slide, but what are DAGs? Directed acyclic glass. Why are they useful in epidemiology? Provides a graphical perspective for understanding epidemiologic concepts involving causation, association, and bias. Where do DAGs fit in? They help you to decide how to specify the initial model, particularly with regard to determining potential confounders. Don't you remember that? I mean, that's sort of where it comes in, okay? And you may remember these pictures. Remember these pictures? That's the start-off part, you know, when Penny started talking about this. And this one says, you know, E goes to D through C. This says C goes to E and C goes to D. This is a situation where you have an intervening variable, and this is where C is a potential confounder, right? So if you had this situation, you don't want to control for C because it's an intervening variable. But if you had this situation, you probably ought to control for C. If your DAG says this, don't control for it. Don't put it in the model. Or don't put it in the model in order to be able to get the right answer about the exposure-to-disease relations. Because if you control for it, you're not going to get the right answer. You're going to find out there's no relationship. So this is a key point about the start. Think about what your DAG is, and in some sense, and certain kinds of variables you're not going to put in your model. So that comes into play in this first part of the modeling strategy. It's not the only thing, but it's very important. So, and that's why I don't spend my whole life thinking DAGs, because it's one part of the process, okay? It's not the only thing, okay? In fact, you know, it can get more complicated. Well, this is where, remember this thing called a collider? You know, I'm sure you love that, right? Collider. Well, if you had a picture like this, E and D goes to C, and C is the collider, well, you don't want to control for C because it's coming after D, right? So it doesn't make any sense. So, but there are some other things we could say about that. But anyhow, if you had this picture, then it gets more complicated when you start, you know, writing or drafting your DAGs. If you had this picture, what would this say about whether you should consider controlling for a C1, C2? And now I have 3 C's in here. Should you control for C1 or C2 or C3 or all of them? And what I say here, these are a bunch of paths. And basically, you can see that if you take any particular one of them, C1 goes to E and C1 goes to D. See the way if you just pick off C1? So C1 looks like it's a confounder from that DAG. So does C2 and so does C3. So it looks like if this was your DAG, you'd probably want to control for all 3 or consider control of all 3. You might not need to control for them, but you would start a model by putting these 3 variables, these 3 C's in the model. And however, if you had this picture, look at this picture. How does it differ? Well, now E's going to C1 going to D. E's going to C3's going to D. E's going to C2. So C1, C2, and C3 are now all intervening variables in the relationship between E and D. So if this was your DAG, you probably wouldn't want to control for either one. Okay? So that's why DAGs are important in order to be considered in the process about whether you should control for them, what should be in your initial model. So, you know, there's a lot more you can say, you can get a lot more complicated, but that's where I'm going to stop on DAGs. And I'm going to go back to this variable specification state and say a little bit more about it, okay? So let's see, how are we doing on the time? Because, you know, when we started the course, Eli was reviewing a bunch of stuff, and he got behind because it wasn't that easy to cover everything, and he sort of rushed what he did with matching. Is that right? Did you think he was rushing it? He wasn't rushing it. Some people, Caitlin didn't think it was Caitlin. You know, I don't know. Everybody's different. So, I feel like I'm rushing too, because if I looked at the schedule, I said, well, Jesus, I'm never going to cover, But anyhow, I'll do the best I can, And if we get behind, we get behind. So, okay, variable specification. Let's go back. Let's make this bigger. Let's talk about that. Okay, well, what do we mean by variable specification? It's that first stage. It restricts attention to clinically or biologically meaningful variables. You just don't put in the kitchen sink, anything that you can think about, the color of somebody's eyes, if it doesn't make any sense, okay? It also provides the largest possible initial model. So what does that mean? Okay, well, first of all, what I'm saying here is, in the variable specification stage, what you're going to do is you're going to say, well, what variables ought to go in the model? And in what form should they go in the model? And once you decide that and you put the form together, you're basically, coming up with a starting model. And what I mean provides the largest possible initial model is, what I mean is, this is going to be a model that's going to, at the most, is going to include everything you want to. You're not going to put for example, if one of the variables is age, okay, you can just control for age by, let's say age is continuous. You're treating it as a continuous. You could put age in the model and control it as, let's say you don't even have, you're not even dealing with interaction. Put age in the model, okay? Okay, if age is continuous, well, why not age square? Well, you put age square in the model. What about age cubed? What about age to the fourth? I mean, how far do you go? Okay? And you might not go too far, because if you do, the model is going to get unwieldy, and what you're putting in the model might not make any sense. If you had a model that had age to the 12th, and the model ran, or you actually even got a model that fit, and it even came out to be significant, what on earth how would you conclude anything about that? How would you make sense out of that? So you don't just put anything in the model, you try to limit it to something that makes sense. And so typically what you're doing is, you're starting with the largest possible model that makes sense. Now, what does that mean about how you're going to get the best model in terms of the strategy? What kind of a model are you going to get as the best model? Is it going to be larger than that model, or is it going to be smaller? Well, it's going to be smaller. If the initial model is the largest possible model you want to consider that makes sense, eventually the right model that you're going to find out is going to be smaller. Well, how are you going to get that model? That's what we're going to be talking about. How are you going to get that model? Are you going to just do backward elimination using this rule that, you can run a program that just says, just go backward one step at a time, just the way it was taught by Bob Lyles. And we'll talk a little bit more about that, but you can do backward elimination. What's the problem with backward elimination? If you have everything under the sun, and that you have the biggest model, but you have confounders and effect modifiers, all sorts of, and exposures, you have all these, and you do backward elimination. Well, you're allowing every kind of variable to compete for being dropped at the model at any stage. You're not considering whether the variable is a confounder, an effect modifier, or something like that. So backward elimination isn't right if you're trying to figure out a best model. So well, according to my strategy, the next step should be interaction assessment. If you got a model that has interaction terms, then you should consider interaction. Okay, that's what I'm saying. So you don't just use an algorithm, but it provides the largest possible model, and eventually you're going to whittle it down by looking at confounding interaction and precision to try to figure out how to whittle it down and come up with the best model. Now, one reason why, so again, variable specification comes first, because that's when you're doing something reasonable according to what the literature says and all of that, and conceptualization. Then I say the next step should be interaction. Now, why interaction prior to confounding? Well, the main thing is that if strong interaction, then who cares about confounding? If you're doing a study and you find that the odds, and you're worried about, you've got an exposure and you've got a disease variable, and then you're worried about controlling for gender, and then you find out when you even just look at the stratified data, or you do some interaction assessment, and you find that the odds ratios for males is very high, and the odds ratio for females relating exposure and disease is almost 1, okay, that's interaction, right? That says there's a big difference in the effect depending upon whether you're effective exposure, depending on whether you're a male or a female. Now, do you want to control for gender as a confounder in that case? Well, you want to control for gender. Why do you want to control for gender? Because the result is the odds ratio, the effect is different whether you're male or female. But if you're trying to assess gender as a confounder, in addition to that, what you'd want to do is come up with some average of these two numbers, that it's sort of average over the fact that you have males and females and you're coming up with some kind of weighted average. Well, you don't want to get a weighted average of two numbers that are giving you something very different, some very different conclusion. So that's why interaction before confounding. That's the main reason. Okay, so the overall average may not be appropriate, may be misleading because you really got different effects. Now, you could get in fact, you can even get something, if you average them, you can get something that looks like there's a strong effect when it's just sort of throwing out the fact that for females there's no effect. So taking an average might be not a good idea. Okay? So, in fact, if this number was a 5.4 and this number was a 0.5, so this is on one side of 1 and this is on the other side of 1, and you took the average, you might get an average of close to 1, which is suggests that there's nothing going on. They're calling me again. And you know, it's always my wife. So she wants to know what I'm going to do for dinner, or something like that. But I know I'm going to fend for myself tonight, so anyhow. So she's just trying to remind me. Okay? So anyhow, if this was 5.4 and this was 0.5 and I got the average and it was close to 1, I might be concluding in some overall way that there's no overall effect of exposure, when in fact there's a strong effect if you're a male and there's a strong negative effect if you're a female. So that's why interaction comes next. Okay? So what about the next thing? What about, but now, by the way, there's always guidelines here. Now, it may turn out, because of depending on where you are with what you're studying, you may not be interested in interaction. You may be at an early stage, and you may just simply want to say, look, I don't want to assess interaction at this point. I just want to see what's roughly going on. I'm hypothesis generating. So I don't want to even consider a model with interaction. Well, if that's the case, skip the stage. Don't consider it. Okay? That's what I'm saying. Proceed directly with confounding. We'll have to talk about how you assess confounding. We'll have to talk about how to assess interaction. So if the goal is to get a single overall estimate, then you might want to ignore interaction. These are guidelines. You have to decide that. Okay? But if interaction is present, you don't want to assess confounding for effect modifiers. If gender is an effect modifier, you don't want to control for it and get an average over the male and female. That's what I'm sort of saying here. However, if gender was an effect modifier, you don't want to get an average, but if you got another variable, race was not an effect modifier, you still might want to control for race as a possible confounder because it's not in there as a product term in the model. We'll talk about that. Anyhow, next issue, confounding followed by precision, the third step. Why confounding before precision? Why not precision before confounding? Well, again, what do you mean by the precision? When you're talking about precision, you're talking about essentially the confidence interval around the estimate you're trying to get. And if you're doing logistic regression, what's the estimate that you're usually trying to get, even though there are different variations on the thing? Usually getting an odds ratio. That's the natural estimate. You can estimate a risk ratio. Eli's going to talk about that later. But if you're getting an odds ratio, the idea is you want to get precision means getting the confidence interval around the odds ratio. And the tighter the confidence interval, what does that say about precision? The better the precision. The wider it is, the less precision. You want to get a tight confidence interval or a wide confidence interval? Ideally, you want to get a tight confidence interval. That means you got a good answer. You got an answer that allows for variation, but the variation isn't that much. That's sort of the idea, okay? Now what this picture shows, the picture says, well, here's a situation where the true odds ratio, or this true parameter that you're trying to estimate, I'm calling it theta, but it's really an odds ratio. So suppose the true answer, the true result that you really want to get, if you actually had everybody that you could study, the entire population, is right here on this line. It's right here. Right here. And it turns out that you did your study and you did it one of two ways. You did your analysis, you did it one of two ways. You did one analysis to give you this is your odds ratio, and you did another analysis to give you this is your odds ratio. Okay, which of these two estimates is more precise? This one, right? Right? Why? Because the confidence interval is tighter. Well, would you want to use this one? This is giving you a tight estimate around the wrong answer, right? So ideally, you want to make sure you're getting close to the right answer before you start asking how tight is it or how good is the precision. You don't want to get a confidence interval about some odds ratio that's way wrong, is what I'm saying. That's what I'm saying here. That's why you want to make sure you got the right answer, which is you're controlling for confounding, before you try to get a tighter confidence interval. I'm being kind of loose here, but I got other things to do, so, that's what I'm doing. I'm going on, okay? Now, another thing about confounding. We're going to get more specific here, but one thing about confounding. When you learned about confounding in 530 and 534, and you learned about how to assess confounding, you didn't do statistical testing for confounding, right? Why didn't you do statistical testing? Because confounding is a validity issue. It has to do with getting the right answer. Validity issue has to do with, remember there are two kinds of error, systematic error and random error? When you're talking about confounding, you're talking about systematic error or random error? Talking about systematic error. Are you estimating the right thing? Okay. If you're doing random error, then you can talk about doing a test. But confounding has to do with are you shooting at the right target, essentially. And that's why you don't test for confounding. Now, you learned in 530 and 534 that if you had a 2x2 table and you had several of them, or you're doing stratified analysis and you're trying to assess confounding, you didn't do a statistical test for it. You went to see whether the odds ratio changed by a certain amount. Remember that? Whether the odds ratio meaningfully changed by, what do you remember about meaningful? What did that mean? That was statistically significant? No. What was meaningful? Well, you had to judge that, but there was a 10% rule. Did the odds ratio change by more than 10%? That's sort of what you had to do there. Now, that's what you did when you were doing just 2x2 tables or just a crude analysis or a stratified analysis. Now, when you're doing mathematical modeling, the same situation applies. If you're not allowed to do statistical testing when you're doing the simple analysis, you're not allowed to do it when you're doing a more complicated analysis, because confounding has to do with systematic bias, whether you're doing a complicated mathematical model or whether you're doing a simple model or a simple analysis. So you don't test for confounding. So what do? Well, what you do is you have to see something about whether the odds ratio changes. How do you do that when you got a lot of variables in the model? Well, we have to talk about that. Okay, so you do statistical testing when you're talking about random error. So confounding and logistic regression is a validity issue, and computer algorithms, which involve statistical testing, aren't good, because if you're getting rid of variables because they're not significant, that's not the way you assess confounding. Okay, although there are some variations on that. Again, I'm going to not talk about that today, but okay. So now. Again, I'm watching the clock here, and I got to make sure I get to where I want to be to a certain extent. And okay, now here I got this slide, and on this slide it says statistical issues beyond the scope of this presentation. Okay, what this means is when you're talking about this whole process of trying to get the best model, well, there's a bunch of things that. I've got this strategy, 3 stages. Well, there's some other things that you also have to worry about somewhere in the process as you're doing those 3 stages, okay? And these are 3 things here, but I'm not going to get to them in any meaningful way until after we talk about the 3-stage process and how you go about that, okay? But the 3 things you have to worry about here, one of them is called multi-collinearity, or just collinearity. or sometimes called, we'll explain the difference between collinearity and multi-collinearity. But that has to do with the issue is that you have a model. You're doing logistic regression. You have your left side of the model, which is your outcome variable, whether you have the event or not. And then you got on the right side of the model, got your exposure variable, you got your C variables, your V variables, your EW variables, all those things in the model. Well, what can happen is that on the right side of the model, some of the variables you put in on the right side, as I say here, can be approximately determined by some of the other variables on the right side. So if you got variables on the right side that are essentially in some collective way are saying the same thing, you sort of overstated your model. You shouldn't have all those variables in there. Here's the extreme way where it really can go wrong. You remember, you learned something about dummy variables? Remember dummy variables or indicator variables? Let's suppose you had a variable, your exposure variable was treatment status, and there were 3 treatments that you were comparing. That's your exposure variable. What would you do if you wanted to run a logistic model? And Eli, I think, talked about this when he was doing examples. How would you write the exposure variable in your model? What would you have to do? And these 3 treatments are very different. They're not ordered. It's not one is more stronger than the other. There are 3 different treatments. You get this kind of pill or that kind of pill, and there are different kinds of pills or something like that. What would you have to do? You'd have to use dummy variable. What does that mean? You'd have to define, you got 3 categories of a variable. How many variables do you put in your model? 3 or 2? 2, right? And these are called dummy variables, 1, 0 variables. And then there's a referent group, right? Which is the 3rd category that you have to decide on, okay? So that's how you do it. You put in 2 dummy variables. You don't put in 3. What if you put in the 3rd one? What if you put in a 3rd one? You put 3 1, 0 variables. So you're in treatment 1 versus none, treatment 1 or other, treatment 2 or other, treatment 3 or other. Those 3 variables. What would happen? Well, it turns out you'd be setting up a collinearity problem. Because it would turn out that once you knew 2 of them, the 3rd one could be determined mathematically from the first 2. And the 3rd one is superfluous. Not only that, if you tried to run the model with the 3 of them in there, it's not going to run. That's an extreme example of collinearity. But there are other examples, and we're going to get into that. There are other examples. You can have 2 variables, age and blood pressure, as predictors in the model, and depending on how you've collected the data, it could be they're very highly correlating. You shouldn't have them both in the model. Or you could have age and blood pressure, and then you put in a product term. Age times blood pressure as predictive variables? Well, it could be the product term is very strongly related to the individual variables that you had. It may or may not be. If that's the case, you shouldn't have a product term in there. That's what we mean by multicollinearity. And when that happens, you either get no results or you get unreliable results. And we talk about that later on just before the midterm, although it's going to be on the 2nd midterm. Multiple testing. The more tests, the more likely significant findings, even if there are no real effects. If you torture the data enough, it'll confess, right? You've heard that, right? If you do enough tests, you find something significant, okay? You remember that? You remember you learned something about the Bonferroni correction? What was that? Bonferroni correction. Let's say you were supposed to do 10 tests. You knew you had to do 10 tests, and you were worried about the fact that if I just did each test at the 5% significance level, I may find out that I wind up getting some things significant, but they're really not because I'm giving myself more of a chance to get the significance. There's really some kind of combined significance level that I'm not taking into account. What's the Bonferroni correction in that case? What would you do? You had 10 tests, and you were doing them all at the 5% level. You divide 0.5 by 10, so you do them all at the 0.005 level. Well, if you do that, the problem with that is you might not find anything significant, so it's sometimes an overcorrection. The problem with modeling is if you're doing modeling, particularly for interaction, you don't even know how many tests you're doing from the get-go. You don't know whether you're going to do 5 tests or 10 tests. So how do you decide what to divide by? So there's a problem with multiple testing. How do you go about doing that? And we'll say a little bit more about that, but actually it's a very sort of an unclear thing how you do that. It's more loose how you deal with multiple testing than it is multicollinearity, although there's some looseness of multicollinearity. Then there's the third thing, influential observations. What does that have to do? Did you learn anything about that in Bob Lyle's course? What does that have to do with? It has to do with the people in your study. You could have 50 people in your study, okay? And you're doing a logistic regression model with put all 50 people in the study, and you get, let's say there's no interaction terms, so the odds ratio is e to the beta, right? The odds ratio is e to the beta if there's no interaction terms. And if you do it for all 50 people, you get a certain e to the beta of 4.2, okay? Now, suppose what happens is you drop one of these people. Somehow you leave out person 43. And then you do the logistic modeling, and you get e to the beta for the model that doesn't have person 43, and it's 2, not 4.3, whatever I said, 4.3 or something like that. Well, that person, dropping that person, influenced the results. That's what's called an influential observation. Didn't you learn something about that? I think. And there are ways that you can do, whether you're doing logistic regression or linear regression, there are some computer approaches to how to put some code in that allows you to determine whether you have influential observations or not. What do I mean by an influential observation is a person in the data set so that if you drop them from the model, it influences the outcome. So you have to have some measure of what you mean by influence. Do you remember a measure? It was called, actually, I'm trying to remember what it was called. I forgot it. Something, it's a measure that you get computed, and if the measure is high, you say it's influential, and if it's not, it's not. Okay. What's it called? I didn't hear.
Cook's distance.
Cook's distance, thank you very much. Okay, Cook's distance. You compute Cook's distance. Well, depending on whether it's a logistic model or a linear model or something, there are measures that are Cook's distance type measures that you compute for every person in your data set. And you decide from that whether you've got influential observations or not. Now, there is this problem. What if, I'm not saying a lot about this, but I'm saying more than, maybe I wanted to, but suppose you do this. You find that there are 5 people in the data set who are influential, that if you took either one of them out or all 5 of them out, you get a very different answer than if you put everybody in there. Okay. What do? You take them out? Or do you leave them in? Well, that's a problem, right? Not everything is, that easy. If you take them out, you're getting a different answer than if you put all 5 in there. Now, if it turns out you find out that those 5 people, the information you had on them were completely wrong. You had their blood pressure, and their blood pressure was 2,000. Something like that, and it's wrong. Well, you have to take them out unless you can do what? Correct it for those people. Get the right number. Okay? Now, if they were correct, if the blood pressures were correct, and they made a difference, well, you have to decide whether you want a person like that who influences it, whether you want them in the study or not. Maybe they had a very high blood pressure, but it was still within the range of blood pressures you want. You can decide, I don't want to have people in my study that are that high, so you drop them. Those are the things you have to do. That's more common sense stuff. So that's influential observations. Coefficients may change if now, there is this thing called an outlier. You know what an outlier is? An outlier may not be an influential observation. What's an outlier? That's a person whose whatever value is you're measuring, one of the predictors, is way out of where, if you're measuring their age. They're 103 years old, okay? And you don't want maybe anybody in there. That's an outlier. Now, whether that person's influential or not in the result it may still not be influential. So an outcome that's a variable or person that's an outlier may still not be influential. So outliers and influential are different things. Now, you don't really want outliers either, but influential observations are the one that most people worry about. But you do have to worry about both. Okay, now, here we go. Let's see. looking at the clock, and we still got a few minutes, more than a few. So let's talk about we've now talked about the variable specifications. So we even talked about where DAGs fit in, okay? So that's when you define clinically or biologically meaningful independent variables to provide an initial model. And as we talked about, as Eli talked about when he started reviewing things, when you're starting the process of model selection or doing a logistic or even a linear model, you have to first start with, well, what are you studying? You have to measure the variables that are the key variables in your study, which is your health outcome, your exposure variable. You may have more than one exposure variable, and all the variables you decide that are important to consider to be listed as variables you want to control for, which are called the C's, okay? And you do that based on the study goals, the literature review, and the theory. So you're starting with the D, E, and the C's, okay? But then you remember in this couple of classes that Eli taught, and I taught last semester, there's this EVW model. So you might, when you start talking about, well, what variables do I control for as either potential confounders or potential effect modifiers, you might want to consider not only the C's, but functions of the C's. Like you may have age, but you might also want to put age square in the model. You may have age and race, and you may want to put in exposure times age times race, or exposure times age and exposure times race, okay? Or exposure times age times race. Age times race, if age is a C and race is a C, age times race is not a C. It's a product of two C's. It's a V, and if you put it in the model as a product term with the exposure variable, it becomes a W. That's, you have to think about all the things. You have to get that down pretty clearly. So that's, so that's the variable specification stage. So what I'm sort of saying is, if you're starting with the D, E, and the C's, in the variable specification, how do you choose the V's? How do you make a decision about the V's? Okay? And it's a loose answer. There's no way I could make it very specific, mathematically specific. And basically, you choose the V's based on prior research or theory and possible statistical problems. Now, what I mean by prior research or theory is, if one of the C's is age and another is race, and if you want to put in a V that's age times race, if that doesn't make any sense to you, you don't put it in. Even though it's a product term. I mean, consider age, race, sex, body size. What about the product of those four variables? Do you put that? If you do that, and each one is a C, the product of those four variables is what? Just by putting them in the model without product with E. It's a V, right? Age times race times sex times body size, not in the model as a product term with E, is a V term. Do you want a term like that in the model? Well, if it doesn't make any sense to you, or you found out that you needed to have the term and you try to interpret it, it didn't make any sense, you don't put it in the model. So you have to think about this when you do it. There's no really great answer to it, prior research or theory. And then when I say possible statistical problems, well, that's another thing. If you put in age times race times sex times body size, putting in this four-way product term in the model, well, that may cause collinearity with some of the other variables you already have in the model. So you don't want to have too many higher order terms because they may be related to some of the lower order terms. And this is a decision you have to make. So as I'm talking to you, you're saying, gee, I want to be a taxi driver. This is too, I'm leaving you too much things to do, But when how am I going to give an exam on any of this? Am I going to just leave it open or something? Well, I'm going to try to lead you through how, suppose the V's are this, and what would you do next, or something like that. So you'll get practice with dealing with this. So if the C's are age, race, and sex, then the V's could be just age, race, and sex. Or the V's could be age, race, sex, age square, age times race times sex, age times sex, or even a three-way product. How do you decide between them? Well, the simplest thing is to choose the V's as the C's themselves. Then you see, at least you're controlling for everything that you decided you were interested in. If you start adding these other variables to the model, you're asking yourself for some problems, but you may decide that I'm interested in age square. Well, how might you be interested in age square, even if age was continuous? Why might you be interested in age square? Because why? or another way to say that is that you might want to, it may be the relationship between age and the outcome. It's not linear. It's not as age goes up, let's say the outcomes, let's say it's linear and the outcome is blood pressure. It doesn't mean as age goes up, blood pressure goes up linearly. It may go up in some quadratic way. And that may mean you should have an age square in the model. Okay, so just because you have age doesn't mean you shouldn't have an age square. Or it doesn't mean you shouldn't have any kind of product term in the model, because it may make sense depending upon, in fact, you can even look at your data as you're making this decision. You could say, well, I'm going to look and see if in my data age is quadratically related to the outcome in some way. And if you do, and you find it, you may want to put age square in the model. So it's not an easy answer, but this is a decision you have to make. So there's the variable specification stage. Now, except I'm not finished, because I talked about the V's. What about the W's? You know, you have to have V's and W's in there. So again, you sure you don't want to be a taxi driver? You know, I don't know whether I'm picking the right field for you, you know. But, okay, so how do you choose the W's once you've decided on the V's? Okay. Well, what I'm saying, well, you know, when you started with V's, the W's are going to be a V times an E, or a variable times an E. And the W is not the product term with including the E, it's just a part of the product term without the E. Right? That was gone over in lab yesterday, I'm pretty sure. I hope that it was. Okay, so I'm making a recommendation here. Restrict the V's to be either the V's themselves or products of two V's. Now that means that if you've decided on a certain V, which could be a C, then you were going to allow E times that V, and maybe you have E times the product of two different V's. But what I'm not allowing is E times V1 times V2 times V3. Why aren't I allowing that? Why aren't I recommending that? Because it's making the model more complicated. And you're asking for, but does it mean you can't do it? There's nothing you can't do. I mean, if you want to have E times age times race times sex, you can do it, but you're asking for some trouble. And you have to decide, if I put that in, can I make sense out of it? And is it going to cause me problems with collinearity or doing any of the testing I want to do to figure out what the best model is? So, and this is just a way of simplifying it. In fact, it's probably not a good idea even to have products of E times two V's. The simplest thing is to have E times a V. Okay? Now, I'm using V's and not C's because, remember, you're starting with C's, but the variables you're really putting in the model are V's, which are allowing for C's, but even more complicated ones. So most situations, you would specify the V's and the W's as either the C's or the subsets of the C's. So if the C's are age, race, and sex, the V's and the W's might just be age, race, and sex. Simple. Then if you do that, then you're allowing yourself for possible confounding and interaction with all of these variables. That's what you're allowing. If you start putting in age times race as a V and you're putting in age times race as a W, then it's more, you got to worry about more things, but you have to decide that. And it's not that easy. So what do you want to do? So the rationale for the W's, again, it's common sense. Product terms as or more complicated than E, VI, VJ, or even just E, even as complicated as E, VI, or VI, VJ, are difficult to interpret, typically cause multicollinearity, so the simplest choice is just to use E, VI terms. So I'm just giving you a guideline on how to do the variable specification stage, but it's still always up to you. Now, there is a question, how do you give a test on it, but that's my problem, you know. How do I write questions on it? But when you have your data, you have to decide. Okay, so at the end of variable specification, this is where you're at. You're at this flow diagram situation where you started with D, E, and the C's, and then you're choosing the V's from the C's in some way, according to what I've recommended, and then you're choosing the W's from the C's as either VI's, that's probably the simplest thing, or VI times VJs in addition to VIs. And so the interaction terms are going to be of the form EVI or EVI VJs or some combination of them. So that's where you're at the start of variables, at the start of the modeling strategy, variable specification stage. You have to make these decisions. It's not easy. Okay? So what do we do next? What do we do next? Well, we actually have to worry about something. You would say, well, the next thing on the list was what? That was variable. So the next thing on the list was interaction. Okay? But there's something else we have to worry about at this stage, which is something I think Eli mentioned, and it might have been mentioned by Bob Laz. It might have been mentioned in, I might have mentioned when I originally talked about logistic regression before, but here's the thing. There's a requirement. There is a mathematical requirement. There is something that you got to worry about mathematically. And this requirement has to do with when you specify that initial model. When you write down what's in that initial model, the E, and right now I'm only considering 1E. 1E, V's, and EV's in the model. There's a rule. The model has to be what's called HWF. Has to be hierarchically well formulated. Have you heard that term? Did Eli mention it? Anybody mention it? Well, I'm mentioning it. I don't know. And it says, given any variable in the initial model, all lower order components of that variable must also be included in the initial model. All lower order components of any variable in that model must also be in the model. But that's the rule. It's really a simple rule. And here's an example of a model that's not hierarchically well formulated. Watching the clock here. Yeah, well, fine. This is a model that's not hierarchically well formulated. Why? Now, you can look at the next slide, but I don't want you to. Let's look at this slide. Here's a model. It's got variables in the model, predictors in the model. And it said, the rule says any lower order component of any variable in the model has to be in the model. What variable is missing from this model? V1 times V2, right? That's a lower order component of this thing, and it's not in the model. Okay? So this is not hierarchically well formulated. I'm just giving you an example of a model. I'm not telling you why at this point. I'm just giving you an example. Okay? And so I say, that's why. It's not because this thing's not in the model. So how do you make it hierarchically well formulated? Put it in the model. If you want to have EV1, V2, and you want to have the model hierarchically well formulated, you better put in V1 times V2 in the model. Otherwise, you don't have a legitimate model. Legitimate, I have to explain that. But I'm just telling you what the rule is now. Here's another example. Is this hierarchically well formulated? Well, the highest order, usually the way you do it, you look at the highest order terms. Okay, are all the lower order components of this term in the model? Yeah. E is in the model, V2. You don't have to worry about V1 times V2 because you don't have E times V1 times V2 in the model. So this model and the lower components of EV1 are in the model. So this model is also, this model compared to the previous one is hierarchically well formulated. So this is a legitimate model. I don't have to add anything to this model to make it legitimate in some sense. Now the question is, okay, so that's what this slide says. Now, why? Why does the model have to be hierarchically well formulated? Now, here's an answer, but I'm going to give you I'm going to describe the answer with an example. The answer is that but I'm going to illustrate it. The answer says, if the model is hierarchically well formulated, if it's a legitimate model, so you've got this model that all the lower order components are in the model, if it's hierarchically, then it turns out that any tests you want to do about any variable, and particularly for the highest order term in the model, go back to this model. What's the highest order term in the model? This one, right? And what I said was any test about this highest order term, there's only one, is independent of the coding of the variables in the model. That's what this statement says. Independent of the coding if it's hierarchically well formulated, and not independent if it's not hierarchically, and it's dependent on the coding. Now, what does that mean? Coding means how you're defining the variables E, V1, and V2. So let's illustrate that. Let's illustrate that with an example. Okay? Here's an example. Here's a situation. I've got an E variable, a D variable, and a V variable, a V1 variable. Okay? Now, if you look at this data, now in this case, D is 1, 0. E could be defined as either 1, 0, it could be any two numbers you want to have. And depending on how you define it, then you're coding it a certain way. If I define E as 1, 0, I'm coding it 1, 0. If I define E as 2, 1, I'm coding it differently, right? That's what I mean by the coding, okay? Now, if you look at this data, and there's V1 is another variable. It might depend upon the coding. If this is 1, 0, E is 1, 0, and V is 1, 0, that's one way to code the E and the V1 variable. But now, regardless of how you code it, when you look at these two tables, is there interaction? Sure enough, right? Show enough, as they say, right? Show enough. There's interaction because this is giving you an odds ratio of 36 for this category, and this is an odds ratio of 1, right? So what does that mean about the model, given this? If you were going to define the model, that's suggesting you ought to have a product term in the model in order to reflect the fact that there's interaction, because that's what product terms do, right? Okay, so here are two models, okay? Here's one model, and here's the other model. Now, I wrote down, this one is hierarchically well formulated, this is not. Why isn't this hierarchically well formulated? Because neither E nor V1 is in that model, right? But this is, okay? And I could decide to code I could decide that to code my E and V variables as either 0, 1 or minus 1, 1, 1, 2. Those are different codings I could have. Or anything I could have with 0 and 100, something like that. Now let me show you what happens. Here's a result from doing logistic regression from these two models, one of which is hierarchically well formulated and one of which is not, okay? Now, look at this model and look at the output. This is the output for this coding, and this coding. Three different ways to code the E variable. See that? 0, 1, minus 1, 1, and 1 and 2. When I fit this model and I look at the output, I've run the models, I'm giving you the output. Notice that the wall, now how would you do this test for the product term? Two ways to do the test. Remember you learned that. One is the wall test, and the other is the likelihood ratio test, right? Likelihood ratio test would be you compare this model with a model that doesn't have the product term. The wall test, you should take delta 1 divided by its estimated standard error and you square it. And that's a chi-square with 1 degree of freedom. Okay. So now I'm just showing you the wall test, and turns out the wall and the chi-square tests are about the same for this model. So it doesn't, and the likelihood ratio about the same. But notice the wall test value for this interaction, same, what do you get? Same number, right? So what can you say if you use this model, and the question is, if you test for the highest order term, is it independent of the coding? Isn't that what this is showing you? It doesn't matter how I'm only giving you 3 examples, but I'm getting the same answer for the highest order term. However, if I use this model, do I get the same answer? No. In fact, these 3 are significant, each of these 3 are significant, so either way, I got a significant result. But it could be, depending upon the data, one of these might be non-significant. But I can't get a difference if I have a hierarchically well-formulated model. That's why it has to be hierarchically well-formulated. Get that? So you have to make sure, if it's not, there's a question back? No, so you're just scratching your nose or something. Okay, so where do we go from here? Okay, watching the time, because, there's still time. Okay, so what do we do? Okay, what we're doing is we started with an initial model, and we're doing this modeling strategy, and eventually we want to get to a final model. And once we get to the final model, we're going to make a decision of what the exposure-disease relationship is, and we're going to say something how strong it is. In fact, there are 3 things we want to get out of the final model. What are the 3 things we want to get out of an analysis? If we're doing any analysis, whether it's a crude data, stratified analysis, or a logistic, what are the 3 things we want to do out of an analysis? Let's assume the measure of effect is an odds ratio. What are the 3 things you want to get about that odds ratio? You want to get an estimate of the odds ratio. What is it? What's the number? How high is it? 4, 1, 22? So you want to get an estimate of the odds. What else do you want to do? You want to get a confidence interval, because what does that tell you? How precise is the estimate? What else do you want to do? You want to test the hypothesis about whether it's significant or not. Those are the three things you want to get out of a logistic regression analysis, a stratified analysis, a crude analysis, a survival analysis we're not even talking about. If you're doing the analysis, those are the three things you want to get that describe the exposure-disease relationship, controlling for the variables. And when you get those three things, what do? Try to make sense out of what it means. Draw conclusions about the relationship. Is there an effect? How strong is it? How precise is it? And that's where you go. So those are the three, no matter what you're doing, okay, those are the three things. Now, so you want to go from the initial model to the final model. Okay, now, the way we're going to do this, we're going to use an approach called a hierarchical backwards elimination approach. That's part of the strategy. But it's how you do it is, I mean, there's guidelines, but there's a lot of room for maneuver here. So you start with the initial model, okay? And then the next thing you do is you eliminate the E, VI, VJ terms in the model if you have those terms. You know, if you've decided that I'm not going to put in any E, VI, VJ terms, E times age times race, there are no terms like that, you don't have this step, right? But these are the highest, and if you have E, VI, VJ, VK, then those are the terms you start off with trying to assess. But let's assume I'm going with my strategy, so I'm not allowing anything higher than E, VI, VJ, so I eliminate them. How do I eliminate them? You see the word testing? See the word testing? What does that mean? How do you do testing when you've got product terms? Or anytime, if you've got a logistic model, how do you do testing? Well, there's likelihood ratio tests and there's wall tests, right? So how do you do it? Well, let's say you had 3 product terms, and you wanted to see if taken together there was anything significant for all 3. What would you do? What kind of a test would you do? I don't know if Eli used the term. I think I did. You'd use what's called the chunk test for all 3. You compare the model with all 3 product terms with a model that doesn't have the product terms in there. And you get a likelihood ratio test with 3 degrees of freedom. Okay? And then if that's significant, you might say, and I think I remember talking about this last spring, if it's significant, you might say, well, maybe I don't need all 3. Even though that thing is significant, I can maybe drop some of them. In fact, even if it's not significant, I might say, if it's not significant, I do the chunk test and it's not significant, and then we'll get to this. If the chunk test is not significant, I might say, well, should I drop everything? Maybe the chunk test was some kind of overall something that's missing something, that maybe one of them is highly significant once I drop 2 others. So anyhow, the first stage is if you got terms like this, you eliminate them using testing, either likelihood ratio or chunk tests or wall tests or likelihood ratio 1-by-1 likelihood ratio test 1-by-1. Now once you do that, you then eliminate the next lower order term. And you notice I say testing, testing, testing. Why do I say testing? Why didn't I say no testing? Why did I say testing here and no testing there? Because this has to do with product terms, which has to do with what? Interaction. You can test for interaction. Interaction is not an issue of validity. It's considered an issue of causal explanation. There's a lot of literature about that. You can test for interaction, but you can't test for confounding. So after you get to this, when you're trying to decide about the VI or even the VI-VJ terms, if you have terms like this, you have to do by no testing. Okay? So that's the process. That's the process you're going to do. Now, how you do this process, we're going to go into the details of that. And I was hoping that today I was going to go through all the details today, and I knew that was wishful thinking. Unless you want to stay until 7 o'clock. No. But this is so interesting. Isn't this so interesting that you really do? But so we'll stop here, okay? And then we'll go on from this. Now today is Thursday, so we're going to start next Tuesday, right? Not Saturday, but what's going to happen, by the way, What's happening on Saturday? My band is playing at Jerry Farber's side door, the intersection of Piedmont Road and Roswell Road, and we are good. But I know you're not going to come, because you have too much work to do. We even have an easy price for students that's cheaper than going to the movies. So if you want to see something instead of going to a movie, if there are no movies, come to see our band. Saturday night.